When stars eventually die, they contract, they get smaller, but their mass stays really large. And so that means the gravity at the surface of those stars gets very, very strong. And so in this lecture, we're going to explore what happens with very, very strong gravity and introduce the thing with the strongest gravity, which is a black hole. Now, first, let's just recap a little bit from last week. We mainly divide stars into two groups, the low mass stars and the higher mass stars. So the sun would technically be in the lower mass star group. Stars that are, twice as big as the sun and bigger, we would consider high mass stars. Now, the mass of a star can change as it goes through its evolution. We learn about things like planetary nebula, where some of its mass gets ejected into space. But the basic dividing line is around twice the mass of the sun. Those stars are higher mass stars, and then everything else below that is a lower mass star. Now, low mass stars will contract until they're supported by electron degeneracy pressure. So electron degeneracy pressure is when the electrons of atoms are pushing back against the further compression due to gravity. And then higher mass stars, which will blow up in a type 2 supernova, will contract even further until they're supported by neutron degeneracy pressure. So essentially what happens is the electrons and the protons are merged because the pressure is strong enough to overcome the electron degeneracy. And then what we're left with is neutron degeneracy. So we get neutron stars. So if you start with a low mass star, you end up with a white dwarf. And those white dwarfs are mostly made of carbon atoms that are at atomic density. So they're just atoms pushed together until they're touching. And that makes them about the size of the Earth. So you have a huge, massive star about the size of the Earth. Even higher mass stars, they can compress even further until they're at neutron density. And they are further compressed down to the size of a city. So higher mass, but smaller star. Okay, so that's a recap of last week. What happens when you have more mass than neutron degeneracy pressure can handle? In that case, we don't know of any other pressure, internal pressure of the star that can save it from complete collapse. And so our best theoretical guess at what happens is that the star's mass compresses into a single point, which we call a singularity, and it has no size to it. It's just a single point in space where all that mass has been compressed into. There's nothing to push back. Now, it may be somewhere down the line that we learn that there's something in quantum mechanics that gives that point, that singularity, some actual size to it. There's some as yet unknown pressure that holds it up. But it compresses past the point where neutrons can support the weight and crushes down basically to a point. And that point creates a black hole. Now we'll get into what those black holes are and the weirdness that surrounds them. I'm sure you've heard at least a little bit about black holes in science and science fiction. And so we'll try to unpack the interesting details and get into what they're really like. Now, the main issue here is gravity, and our concept of gravity is going to have to change pretty dramatically to understand these massive objects compressed down to very, very small size. Gravity gets so strong that our previous understanding of gravity isn't good enough to explain the observations, the things that we can see happening in space. So let's just quickly think about the gravity of objects that we do have some familiarity with, the Earth and the Moon. Gravity obviously keeps us stuck to the Earth. The gravity on the Moon is weaker. So when we sent astronauts there, they were bouncing around feeling very, very light because the gravity is about 1/6 of what it is on the Earth. So you can ask, why is the gravity weaker on the Moon than on the Earth? Well, how do you make gravity strong? You need more mass and a smaller radius. Well, the moon has the smaller radius, but it has much, much less mass, and the net result of those two things together gives the moon weaker gravity than the Earth has. All right, so now let's think about the stars, the white dwarfs and the neutron stars, the end states of low and high mass stars. Well, a low mass star becomes a white dwarf the size of the Earth. A high mass star becomes a neutron star the size of a city. So the neutron stars are both more massive and smaller. So that means they're definitely going to have stronger gravity than white dwarfs. But white dwarfs, they're the size of the Earth, but they're the mass of like the sun. And so they're going to have much stronger gravity than the Earth. So if you were lining them up in order, the moon is the weakest gravity, then the Earth is about 6 times stronger gravity, and then we have the white dwarf, which is the mass of the sun at the size of the Earth. It's going to be much stronger gravity than the Earth. And then we have the neutron stars, which are the size of multiple suns, compressed down to the size of a city. And so for two reasons, its mass and its radius, it's going to be much stronger gravity than the white dwarf star. And then the logical conclusion here is that if you take the mass of multiple suns and compress it down to a single point, then you're maximizing the gravity. You're getting the strongest possible gravity, and that's the case of a black hole. Now we can put some numbers on it, and I think this is helpful for really understanding, appreciating how we can measure how much gravity there is. And we do that by calculating this number, which we call g. And it involves the mass and the radius of the object. And so let's look at the formula here. And this is the general formula for calculating the strength of gravity, which we call g. It's also known as the acceleration due to gravity, the rate at which things speed up as they fall to the ground, or the surface, whatever. If it's a star, it wouldn't really be ground. But it's the rate at which things speed up as they fall down to the surface. So more mass, bigger g. Smaller radius, bigger g. Now, in the case of the Earth, we'll just measure things relative to the Earth. It would have a mass of 1 and a radius of 1, and so its g would be 1. Now, what about a white dwarf? A white dwarf is about 330,000 times more massive than the Earth, but it has about the same radius, so it also has a radius of 1. So that makes it 330,000 times stronger gravity than the Earth. When we get to a neutron star, its mass is about 660. Now this can vary, obviously, but let's say it's about twice the solar mass. Then it's 660,000 times the mass of the Earth, and its radius is only 0.0016 times the mass, thus times the radius of the Earth. And when you do that, you get 260 times 10 to the 9. Times 10 to the 9 is a billion, so that's 260 billion times stronger gravity than the Earth. So we can think about the strength of gravity by this number, this g. It's the same g that you would hear in like movies when when people are riding in jets. They talk about the g forces. That's the same thing. It's expressing sort of a force that's exerted on your body, and normally it refers to the gravity force on your body that's keeping you fixed to the planet or making things fall to the surface. So for the Earth, we're used to a gravity of 1, or we can measure gravity and call it a gravity of 1. If you were able to stand on the surface of a white dwarf, you'd be compressed 330,000 times stronger, and on a neutron star, you'd be compressed 260 billion times stronger. Now, how can you take this formula and apply it to a black hole? Well, you kind of can't. The thing you divide by is the squared radius. What if the radius is 0? And in our theory, the radius is 0. If you divide by 0, you get infinity. So essentially, you'd have infinite gravity at the surface of a black hole. And so we need to think more about the boundary. What is the real boundary of a black hole? The image here is a very recent one. It's taken in 2019. It was a pretty big news story in the science community, so you might have heard about it. But this is the first ever real picture taken. Now, black holes have been observed, quote unquote, observed indirectly for a long time. I believe the observations that gave some indirect evidence go back to the 1970s. But we'd never actually taken a direct picture, like found an object in space and said, that's a black hole. Let's see what it looks like. Snap a picture. Now, it wasn't that simple in this case either. There's a lot that went into figuring this out. But this is a black hole that resides at the center of a galaxy, a different galaxy than our own, M87. And it looks sort of blurry, and you might be unimpressed by what the image shows you. But there's actually a lot of interesting detail here. All these little blurry regions and this bright sort of crown around it with a brighter region down here. All of these things are predicted by the theory of gravity near a black hole. So it's quite an impressive image when you understand the science that goes into it. Now back to the idea of a boundary. So if the mass compresses down to a single point, then its radius is 0. It doesn't really have a boundary. But there is an area around it which we can think of as the boundary of a black hole. And that has to do with the information that we can get from the black hole. And I'll explain that a little bit better in the next slide. So in order to explain that, we need to introduce a slightly different way to measure how strong gravity is. And these are just alternative ways of thinking about it. Now, the first way was how fast things will speed up as they fall to the ground. This next way is the escape velocity, how fast you need to be going to escape the gravity of the surface. So we call this escape velocity. When we blast a space shuttle up off of the Earth's surface, we have to have it reach escape velocity so that it can leave Earth's orbit. For Earth, that escape velocity is 25,000 miles per hour. So that's how fast something needs to be going in order for gravity of Earth not to be able to turn it back around and pull it back to the Earth eventually. It will keep going. If it's 25,001 miles per hour, it will eventually get infinitely far away from the Earth. Now, what about a black hole? There has to be an equivalent thing for a black hole, an escape velocity, how fast you need to be going to escape from the pull of the black hole. Well, the theory here will tell us that we reach a law of nature, a speed limit of nature, and that's the speed of light. So the escape velocity for a black hole is the speed of light. So in order to escape a black hole, you must be going as fast as the speed of light. And that is for a particular boundary that exists around the black hole. Once the mass has compressed down to a certain size, and you've reached this critical size, the escape velocity is the speed of light, which effectively means nothing can get out. No light can get out, hence the name black hole. Now, they weren't originally called black holes. This was a name given to them by one of the researchers who was really like a massive figure in training future researchers to study black holes and contributed a lot of it on his own. His name was John Wheeler, and he gave the term black hole for this reason that nothing, not even light, can escape from this point in space. Once the mass has compressed down to this critical size. And that critical size is called the Schwarzschild radius, after another researcher who worked out the mathematics and figured out what the size of this thing had to be. And there's a formula for this, and I'm just giving you the approximate version. It's a little oversimplified, but it'll work for us, that the Schwarzschild radius for any object, it could be any star, is 3 kilometers times the mass divided by the mass of the sun. So its mass measured in how many times the mass of the sun. So if something's twice the mass of the sun, this number would be 2, and you would get a Schwarzschild radius of 6 kilometers. What this means is that if you took twice the mass of the sun and compressed it to a size of 6 kilometers or smaller, you'd have a black hole. It doesn't tell you that that's necessarily going to happen. It's just, how could you make a black hole out of whatever the mass is? Let's say something was 1/10 of the mass of the sun. Then this would be 1/10, and this would be 0.3 kilometers. So to make a black hole out of something 1/10 of the mass of the sun, you'd need to compress it down to 0.3 kilometers in size, in radius. So if the mass of something is compressed to small enough size, its escape velocity will reach the speed of light, and it will be a black hole. Now, there's what's theoretically possible, and there's what actually happens in nature. And right now, the way we understand it is that stars twice, 3, 4 times the size of the sun, they're capable of getting the gravity strong enough to overcome neutron degeneracy pressure and become black holes. And so something like the sun won't become a black hole, but the formula will allow you to calculate how small it would have to be compressed in order for it to become one. Now this boundary, this imaginary line that's at the Schwarzschild radius, is interesting, and we'll have to wait for the next video to really understand what's happening there. But essentially it marks a horizon, and so it's called the event horizon. It's this imaginary line where the things cease to come out of the black hole. So if you look off into the distance, it's where the light drops off, essentially. So if you're looking off in the distance at a black hole, that event horizon is where the information stops. And in the next video, we'll get into a little bit more about understanding what's happening with space and with time at the event horizon of a black hole. It's very, very fascinating. Okay, so let's take a quick look, a quick assessment of what we know about the black hole relative to the event horizon. Now, inside the event horizon, because the escape velocity would be greater than the speed of light, we can get no information out, and that means we have no idea what happens inside the event horizon. And according to the theory, it's actually impossible to know. Information can't come out, then we can't learn about what's going on inside the event horizon. How about outside? Well, outside we know the gravity is very, very strong. It's not infinite, so we are not at a 0 radius at the event horizon. We're at something like 6 kilometers in size. So we're compressed down to a pretty small size, and we're taking a very, very large mass. So the gravity is very, very strong, but it's probably comparable to what a neutron star's gravity is near the event horizon, maybe a little larger. And then the next two things I'll say now, but we won't really understand them until the next video. First is space is very curved, and second is time is very slow. So our conception of gravity, as I said earlier, is going to have to change, and the way it's going to have to change is by changing our conceptions of both space and time. And these are not intuitive things, so it will take some mental work to really absorb what's happening here and understand the theory that describes what's going on, which is the theory of relativity.